Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
First, I want to mention I spent the fall semester here on sabbatical in the NLP group with Meg and Lucy, and I had a great time. So if any of you are considering that, I definitely recommend it. So for relevant to the topic of the panel today, I chose some of my recent work that we've been working on, the so-called knowledge-based population problem, in particular using stacking ensembles to do better on the knowledge population task. So first, I want to recognize my students who work on this with me, Nazneen, Vidhun, and Yinan at UT. So KBP is a recent sort of series of evaluations that NIST has organized where you have to extract relational world knowledge from natural language documents. And there's a bunch of different tracks within KBP, and the one that we've been focused on is called English slot filling, which is you have to pull out slots of information about people and organizations. There's also entity linking and some other tracks within KBP. But this is probably one of the more popular ones, is this so-called slot filling task, where you're given an entity like a person like Barack Obama, and then you have to fill certain slots, like where was he born? That's controversial, but we know it's the United States. You know, who was his spouse? Who are his children? Things like this. Or you're given an organization like Microsoft, and you have to, by reading documents, figure out that, oh, it's headquartered here in Redmond, and you know its website is Microsoft.com, and it has certain subsidiaries and so forth. There's one extra interesting thing that when you compete in this competition, you have to provide not just answers to slots, but you have to provide what's called provenance. Where in the corpus of natural language documents did you get that information? And so every answer you have to give the document and a substring within that document that supports that information. So here's an example of where maybe I got the idea that Microsoft is headquartered here in Redmond. So you have to give the actual string in a real document where that belongs, and that's called provenance. There's another subtrack within KBP that's related to slot filling called slot filler validation. And the aim there is you're given the output of individual systems that somebody else has built, but your task is to sort of improve them by editing their output. And initially, this was just meant to take an individual system and improve its precision. So say I have a previous system that made a mistake, like it thought that Malia was Barack's spouse rather than his daughter, and then maybe the system learns to filter that out. But a bunch of people competed in this competition have also basically done ensembling, because they're combining the output from multiple systems. So the idea of ensembling has a pretty long tradition within machine learning, and it's shown to be a very powerful idea. We really get a lot from having diversity of different responses. So there's a whole area where we take multiple systems, take their output, combine them in some way to produce a better output for the system. So we were particularly trying to apply a fairly old idea, but very flexible idea, originally developed by Wolpert in '92, called stacking. Where the idea of stacking is, how do we do that combination function? Well, it says, well, let's solve it as a machine learning problem. So let's train another machine learning classifier to combine the outputs of a bunch of other systems. And that's this idea of stacking. So for each possible slot fill, so say we have a slot fill like, Michelle is Barack's spouse, we get confidence from all our individual base systems, and we used other systems that competed in this competition as our base systems, and we train a classifier. We used an L1 regularized linear SVM, but that's a technical detail. You can use different classifiers there. We didn't see huge difference, but we found that worked the best. And it combines all those outputs to create a consensus decision. We added a couple of interesting ideas to this, which is, well, once we were training a meta classifier, why don't we include other information than just the output of the systems? And particularly, we said, for this relational slot filling thing, what is the slot type? Because different systems might be more confident. One system might be better on spouses, and others do better on children or something. So we want to take that into account. And we said, well, for KBP, people not only provide their answers, they provide provenance in the document where that answer came from. Can we use that information to improve our ability to combine the systems? So we added additional features into the stacker to include the name of the relation and the provenance information. And we use two types of provenance information. So this is sort of the interesting addition on top of just normal stacking, which I think is sort of interesting, where we use document provenance, where the idea is for a given query and a slot, for each system, there's sort of a document provenance feature that gives me information. How much does it agree on where this information is specified in the corpus? So if you have n systems, and say some little n of them have the same provenance as that particular system I has, then it gets a fractional score for that document provenance. That's how much it agrees with other systems on where it got the answer to that system. And that could help us decide how to combine that information. And we also use what here we call offset, or the actual substring information. So I said, well, it's also not just you got it from the same document. Hopefully you got it from the same part of the same document. So we also look at the overlap between your system's provenance and other systems that extracted that same answer. And we use Jacquard similarity here, which some of you might be familiar with. It's just a measure of sort of overlap that takes intersection over union. And we're defining this over strings rather than sets, but hopefully you can sort of easily generalize the notion of intersecting two strings and taking the size of the intersection of their two provenance strings, dividing it by the union of that. Hopefully that's reasonably clear what that means. And then calculate that as a percentage. And each system gets a score also with what substring it agrees with other people. So we put all these features into a stacker to try to combine the best results for this competition. So for stacking, you need some training data before your test data. So what we did was there were 10 systems that competed in this competition in both 2013 and 2014. We trained on their results from 2013, and then we independently tested it on the 2014 competition, which was held last summer. And that's a list of the systems that were shared between 2013 and 2014. Within KBP, there's this other separate track that I mentioned called slot filler validation. And there we actually combined all the 17 systems and 17 teams. Each team can submit multiple systems. There's a total of 65 systems. So that gives us just ensembling over all of the 2014 data. We compared to a number of baselines. Two very simple cases we said was, well, let's just combine the systems doing union. Just take all their results and combine them together. There's some technical detail about whether the slot is so-called list value, where it can have multiple values, or whether it takes a single value. We did some things there. And then another very simple way to do ensembling is just voting. How many systems need to agree on an answer for you to accept it as a real answer? That tends to maximize precision. And we set a threshold of how many systems need to agree to accept an answer by training on the 2013 data and then using that threshold on the 2014 data. So just to quickly get to some results, I think there's a little bit of intellectual contribution here to the algorithm by adding provenance information into stacking, which I think is sort of the algorithmic innovation. But the real reason why I thought this was interesting is the results were quite remarkably good. We got really great advantage from using this stacking approach as opposed to other ensembling approaches, using the provenance information, combine all this together to get really the best results so far on this slot filling competition. First, some baseline results. If we just used all the systems in 2014 to combine their results using a simple idea like union or voting, it improves the results. And not surprisingly, union gives you really good recall. And maybe for those who are not familiar with the metrics here, precision is out of all the answers you produce, what fraction of them are right. Recall is out of all the answers you should have produced, which percentage did you get? And then F1 is the harmonic mean, which is usually the sort of bottom line performance metric that people use in this task. So union's very good on recall. By just throwing in all the answers, you get a lot of the right answers, but you also get a lot of wrong ones, so your F score isn't very good. It's just 12% here. Whereas voting tends to maximize more precision. You have to, a fair number of the systems have to agree before you accept the answer, so more of the answers are correct, but you're losing on recall. So again, the F measure is better, but not great for those sort of ensembling baselines. But then we compared a bunch of different approaches on the actual 2014 English slot filling task for the KBP competition. And this is just using the 10 common systems between 2013 and 2014, because we have to use the 2013 data to train, and we need to know how to train those 10 systems that were shared between the 2 years. And the systems change a little bit from 2013 to 2014, but our results show that even though that's true, what you learn from 2013 data is actually still very relevant to the 2014 competition. So the best results this past year on KBP ESF were from Stanford, and they got an F measure of about 39%, which you notice is not that great. This competition, the results are a little, less spectacular than you might like. And we showed by stacking, you can increase that to 48%, and then a little bit more if you add the actual feature of what relation it's extracting into the stacking algorithm. And then by adding the provenance, you even get another boost. So by actually knowing not just what answers were produced, but where it got those answers and letting the learner figure out how that's relevant to the right way to combine the result, actually broke us through the 50% F measure. And this is the best result, at least that I've seen on the 2014 ESF, is by using this stacking idea with provenance and using the relation information, we get a total F measure of 50%, which is the best results that I've seen on this, this competition. So we're hoping to do this year's competition. We're ramping up to take a bunch of ensembling of systems and actually compete in this year's 2015 competition and see how well we do. There's also results within this slot filler validation track within KBP where people specifically are doing other ways to ensemble and combine the results of multiple systems. And so we evaluated on this. The metric here, I don't want to go into the details of how this metric differs, but it's a little bit different than the actual metric that's used in the competition. Then if you notice, the numbers are a bit higher overall because the metric used in this track is a little bit different and a little weaker. So again, there's the baselines for just union ensembling and voting ensembling. And then here's the results that we got by taking our various approaches. So within this track, which is a slightly different track where every system is doing some sort of ensembling and combining results, the best result came from Illinois last year, and they got an F measure of 48%. And we showed by doing stacking plus the relation plus the provenance, we were able to boost that quite a bit, up to 60% on this task, which again is now, as far as I know, the best results on this sort of evaluation that's done in the so-called slot filler validation track at KBP. So I think overall it shows that this idea of using stacking together with provenance information is a great way to combine multiple systems results and get state-of-the-art performance. So just to wrap up then, a stacked metaclassifier beats the best performing KBP system from 2014 by an F1 gain of 11 points. And if you don't work in this area, you might not realize an F gain of 11 points is huge, actually, in this sort of area. So that's, I think, why I like these results, is it actually gives you a remarkable improvement. And it's not just generic stacking. It's adding in provenance information, which the KBP systems have to provide as part of the competition rules, actually gives you a further advantage. And then we tried to show that just any ensembling technique is not as effective. It's actually using machine learning itself to learn how to combine all this information appropriately to get the best results using both provenance and the system results. OK, so I'll stop there. And I still have 2 minutes left, so I should have plenty of time for questions. I tried to keep it short. Okay, it's a little hard to see up here. I got lights in my eyes.
Yes, very quick question here. Do you have insight into why stacking method is doing better than some other assembling method like boosting or etching?
Well, I think it's just the flexibility that it's actually learning how to combine. It doesn't have just like some fixed strategy like union or voting or something like that, but it's actually figuring out, oh, this system does better on that slot when it agrees with other systems or on where the answer came from, whereas that system does better on that slot, and it doesn't matter whether it agrees on the provenance information. So it's just taking all that information into account and using the power of machine learning to figure out the optimal way to combine all that evidence into a final decision, which I think is the whole strength of stacking. It's sort of like, physician heal thyself. Machine learning, you have a problem, well, what's the solution? Use machine learning to solve the problems with machine learning, which I think is, so I think stacking is actually a very powerful idea. I assume a bunch of you know machine learning and are familiar with it. Like I said, it's an old idea. And but as far as I know, no one else applied it to these sorts of problems, and it works surprisingly well.
I also had an insight question as well. In the two different experiments, the first one, adding provenance actually decreased precision, but it increased the recall, and then so you got a better F score on that. But in the second one, it was the opposite. It had no effect on recall, but it helped precision. Is there any insight into why the provenance helps and hurts in those cases?
Yeah, I don't know. I mean, I think I understand in the first case why it's improving recall, right? It's just by combining multiple systems and deciding when to accept them, and again, it's trained to optimize F measure during the training process. So, and it decided that better recall was a better trade-off there is basically what the SVM is learning at the stacking level. But why that's different in the second, I didn't actually notice. I'll have to look into that more. It's an interesting point.
Yeah, great talk. I was wondering whether your methods are always going to choose one of the answers that one of the original systems produced, or whether it can use evidence and say that they're all wrong, but here's the answer.
No. So, I mean, ensembling techniques are only as good as the individual members of the ensemble. So it has no way of creating a new answer out of whole cloth. All it can do is combine evidence for answers that other systems are producing. And so, that's a fundamental limitation, which puts a fundamental upper bar on how well ensembling can help. But again, it's totally compatible. Hopefully now, as each system's years get better, ensembling does even better still. So but no, it cannot produce answers that the individual systems do not produce as candidates. Yes.
So thanks. That was interesting. It seems like you're getting value by seeing how much the derivations behind the final answer agree.
Yeah.
But it looks like, I think right now you're only taking the derivation that was used to construct that one best output, right? Do you think it would be interesting to try to get the other methods to come up with a derivation, or see how much they agree on the derivation or the provenance that led to that?
Yeah, I mean,
instance?
so the only thing, I think, obviously we could ask systems to produce more information, but the only thing we have from the competition is the document and the slot fill, the start and end string. So I think it'd be interesting if we had more information from the underlying systems about how they got to that answer, and the underlying, maybe features that were relevant to them making that decision. That might be additional information we could use. I think that's a nice idea, just we didn't have access to that for the systems that we were ensembling.
I think in the interest of time, we might want to, maybe one more question.
So my question is, you can use, voting is one method to do this, but you can also use voting as features as your machine learning classifier. I've wondered if you've used this.
Well, in a sense it is. I mean, it has all the individual outputs, which in itself, it could compute a vote. I mean, the stacker could learn to just do voting if it thought that was the best thing to do, because it has the representational power to represent a voting function over those inputs. So it just gives you, in some sense, more flexibility.
Okay, great. Let's thank the speaker. And next up, we have Dan Roth from UIUC.
Okay, thanks a lot. I can't see anything, but hopefully you can hear me. So I'm going to talk about natural language understanding with common sense, or I could have titled it Natural Language Understanding is Common Sense Reasoning. And just to get you started, I'm going to start with a puzzle that you have to look at and understand. Is it possible to turn off this projector just in front of me? Or? Well, so something is written here. What is it? Yeah.
Best we can do. We need to capture you. So can you see the audience?
A little bit.
They can see you.
Yeah, I can see the front row.
Yeah.
So, and the front row got the answer. So turn off your laptop. Very nice, very quick, actually. So you do have common sense. And it's quite amazing to me every time with a new puzzle that people get it so quickly. My kids are very good at it. They have a lot of training. And to me, this is kind of like natural language understanding. And if you think about what you've done in solving this puzzle, you've done a lot of things. You identified unit, you looked at multiple interpretations of this unit, because each one of these components can have multiple interpretations in different contexts. There are multiple representations here. Some are picture, text, spelling, phonetics, and you somehow put it all together. And you put it all together in a way that makes sense, that satisfies some of your expectation for what is a coherent or sensible output. Given that I put it all on one slide, given that I told you that it means something, and given, just your expectation of what is a good answer here. So a lot of natural language understanding, I think, is just like that. And the task for us is to figure out how to write programs that can do it. So I'm going to give you a few examples where something like this is being done also in the context of language. So here is a very simple example here. Dan is flying to Philadelphia this weekend, and so on. And then you can make a lot of inferences from this initial statement. One of them is that Dan is attending the workshop. And I would, if I take a vote, I think most of you would agree that this is a legitimate inference here, even though it's not stated here in any way. The workshop is in Philadelphia is another legitimate inference here, even though it's not stated explicitly. And this is part of your expectation for why did people put these two sentences together, one following the other. There are some conventions and some reasons for us to understand that this is what it means. So really, our interpretation of the sentence built on some expectations that in turn rely on a lot of knowledge of convention, knowledge of language, knowledge of the world. And you can think about using this knowledge in many, many other ways. Here is one other inference that you can make. Jan is a black Dutch man. You could infer that Jan is a black man. On the other hand, if I would say Jan is a short Dutch man, probably the inference that he's a short man is not necessarily the right one. Because, Dutchmen perhaps are taller than others. At least you would argue about this. So these are type of inferences that we make all the time in many contexts, in different phenomena. It's even more interesting to think about it when you have more text. So here is a short news stories. And if you try to think about what does it mean to understand this and draw inferences, there are many, many inferences that you can draw from this short story. And here is one of them. Again, most of you would agree that you could say that 49 people were hit by a suicide bomber. And why is that the case? Why would you say yes? Well, 49 people here is justified by this 14 here and 35 here. 35 what? No, it doesn't say 35 people, it said 35 injured. What if I change the injured here to visitors? Visitors is closer to people than injured, but it completely changes the inference you can draw here. And this is just one thing that you have to think about here. There's a lot of other things you have to think about. It says at least. It also says about. What does this, how does this impact the inferences you're making? It says killed and it says hit by and so on. So there's a lot of small things that you have to do here in order to actually agree on the conclusion. And there are many more. In fact, the defense ministry said that, and who knows whether we believe the defense minister or not. So we have to do a lot of things here, a lot of small problems, and to put this together in a way that makes sense to us and to the specific problem. And this is what I want to call the inference problem, and I want to connect this to the way we think about common sense reasoning. So the bottom line is that given this example, I'd like to think about natural language understanding as a type of decision that we were making that are global. They deal with a lot of things, but they require making a lot of local predictions that are driven by different models, trained in different ways, at different times, different conditions and scenarios and so on. A lot of the information that you used in solving my puzzle, most of it, in fact, is something that you brought from home. You don't even know when you were trained to identify this and to make these decisions. It requires also the ability to put these predictions together in a coherent way. And it requires knowledge that guides the decisions so they satisfy our expectation. So expectation here is really a knowledge-intensive thing. You need to know a lot in order to develop expectations. So I'm going to focus here on coherency and satisfying expectation as my running definition of what do I mean by common sense. Developing this expectation and developing models that can satisfy expectations is what I want to think about as common sense. So the thesis I'm going to develop in the next 10 years or so, 10 minutes or so, 10 years too, is that natural language interpretation is a common sense driven inference process that is best thought of as a knowledge constraint optimization problem. And this has to be done on top of multiple statistically learned models. So one small caveat is that, of course, inference itself is a loaded word. There are many forms of inference, and I'm not going to touch all of them. But a lot of them boil down to determining the best assignment to a collection of variables that we care about, and this is going to be my running definition and my interest in the next few minutes. So of course, I'm not the first one thinking about common sense reasoning as this kind of global inference task. There's been work over the last 50, 60 years. Many good people contributed a lot of important thoughts to this line of work over the last 60 years. But I think that they had one common flaw. And this is that they all thought about common sense reasoning and formulated it as something that is independent and irrespective of the learning and the knowledge representation that results from the learning. They thought about it as kind of independent process that someone gives it a representation, deal with it. The only principled study that I know of that actually deviates from this line of thought is actually the work that Ronnie Cardone and I did 20 years ago now, part of my PhD thesis on learning to reason, where we gave a principled account of why is it the right thing to actually put learning and reasoning together and think about it together. In fact, we proved a few things that show why is it essential to think about it this way. Now, this was in order to prove something in a very narrow context, but this is certainly drives what I want to talk about today, which is what's needed is really to be able to think about knowledge, learning, and how these feed into a reasoning process and interact, in fact, very important, with a reasoning process to achieve what we want to do in natural language understanding. So in the rest of the next few minutes, I'm going to suggest a computational framework that does this and give you two detailed examples, or relatively detailed examples, where common sense reasoning actually comes into play in natural language understanding. So my first and very simple example that hopefully many of you have seen already is going to be that of identifying entities and relations together. This is actually work of my student who may be in the crowd here, Scott Yee. And really the goal here is to identify entities and relation between them, and I'm giving you here a cartoonish version of this talk. So of this problem, any way you want to think about it, you want to start by learning a model, in this case conditional probability tables that have some view on these things. And once you want to make, now that you want to make a decision on this, one option is to choose the mode of this conditional probability distribution, these blue lines, and now I have a decision. If you look at these decisions, you'll see that it actually does not make sense. Right? So if you look at these three boxes, you see the two people interact in a relation that is born in. We know that this doesn't make sense. I want to change it somehow, and I'm going to change it by changing one of the entities. If you look at these other three boxes, again, you see that it doesn't make sense for the same reason. In this case, I'm going to change the decision differently. I'm going to change the relation. So, of course, this improves the results if you do this kind of joint inference. And the question that you want to ask yourself, though, is how to learn. I'm not going to talk a lot about learning, but there's a lot of understanding today that you can learn this many ways, separately, jointly, and it depends on a lot of other things that I'm not going to get into. But most important, and what I want to address here is how to guide this global inference. And clearly, there has to be some kind of an objective function that incorporates the learned models with knowledge, which I'm going to call constraints on the output, and I'm going to call this model a constraint conditional model. So in natural language processing, we all got used to thinking about linear models or log linear models of the type I see here, where what I have here is a collection of features or classifiers, if you want, or log linear models themselves, and a collection of weights that weigh these models. And this is how we make these decisions. I'm going to add another component to this linear model, which is going to allow me to model knowledge. And again, I'm going to weigh it with a collection of parameters, if you want, penalties for violating the constraints. And I'm going to think about these constraints as modeling how far is my assignment, my predictions y, from a legal or an expected assignment. I'm going to use the word expected here to actually deliver the point, the relation to common sense reasoning. Of course, there's also the learning component that I'm not going to talk about a lot. Learning here is learning this W and U. And there's a lot of understanding today of how to do this learning. But and I'm not going to talk about the technical aspect, but you want to think about this learning as a way to push the learn model so that it better satisfies our output expectations. Or you can sometimes think about it as a better way to push it so that it better satisfies our expectation from some latent representation. Another thing to think about is you can think about this objective function actually as an integer linear program for the same price. And it's a very, very expressive formulation. You know, if you want to think about probabilistic representation, then any map problem with respect to any probabilistic model can also be formulated this way. So one thing that you may want to think about is, why do I separate this left side of the objective function from the right side of the objective function? And in fact, all of the examples that I'm going to give in the next few minutes really address this thing. Mathematically, they could be the same, but I want this C of xy to actually express high-level declarative knowledge, often first-order logic type knowledge, over statistical model. I could give a few examples, but I'm going to skip these simple examples so that I can move to the examples that I wanted to spend some time on from natural language understanding. My first example is going to be coreference resolution. Hopefully, most of you are familiar with what coreference resolution here. Here is a short story. And one thing that you want to look at the beginning is to see how many names and how many pronouns are there even in short story. This is something that we do all the time, instantaneously, without even thinking about it. Even though in this specific case, if you think about this, it's actually a collection of hard coreference decisions here. There are two Chris's here. One of them is the father of the other. You have to identify it and reason about it to understand it. But more importantly, there's a lot of pronouns here. It's a big problem. It's essential for us to understand how to resolve each one of the pronouns in order to understand the text. And it's a problem that requires learning and inference models and a lot of knowledge. Over the last few years, there's been a lot of advances in coreference resolution. I mentioned here a few of my students that worked on it over the last few years and made a lot of progress. I'm not going to talk about the system that we now have. It's a really nice system in terms of performance. I want to focus on what I call hard coreference problem, and specifically pronoun resolution problem. So if you look at these three examples, you will notice that they use the same vocabulary almost, with tiny changes, but these tiny changes actually mean that the coreference decisions here are very, very different. She is associated with Tina at the beginning, then with Joanne, and then again with Joanne, just with slight differences in the text. How do we do this? It turns out that even state-of-the-art coreference model actually cannot resolve these kind of problems. You really need to know a lot in order to understand how to resolve these problems. And it's important to realize that it's not only lexical knowledge that you have to know. You really need to know the structure of the sentences, who does what to whom. But lexical information is important. If you look at this example, depending on whether I chose the verb to be had or wanted, I want it to link either to flower or to bee. And you can say, you know, if I read enough text, I know that probably bee wants and a flower has, and therefore I can solve it. However, with this example, John Doe robbed Jim Roy. He was arrested by the police. You can see that the type of knowledge you need to know and incorporate into your decision in order to resolve this is really a lot more sophisticated. You need to know that the subject of rob is more likely than the object of rob to be the object of arrest. This is something quite abstract that you have to be able to extract and of course use. So we acquire this knowledge in something that we call predicate schemas, and we're going to use this as a way to resolve this kind of problem. Of course, it requires an inference framework that can make use of this knowledge, and I'm going to use the same formulation, kind of unified formulation that I introduced before, as a way to do this. So the standard way today, or at least one of the standard ways to solve coreference resolution, is to use this ILP formulation, where what you do is you sit on one of the mentions, V, on your right over there, and you think about which of the antecedents should be linked to V, and you formulate it with this collection of objective function and constraints, essentially this is something that is called the best link approach, where when you sit on a mention, you consider which of the things that are on my left is the best one to link to. We're going to augment this with a collection of what I call predicate schemas. These schemas that encode the fact that B wants and flower has, but also think more abstract like the object that Rob and Arrest like and the subject that Rob and Arrest like. And we're going to incorporate these predicate schemas as constraints into our formulation. So essentially, in real time, as I read the sentence, I'm instantiating these predicate schemas with the text of the sentence in the right way, and on the fly incorporate it as constraints into my ILP so that they will support my preferred interpretation, or they will support the expected output that I want to see, something that makes sense. Overall, this approach gives a state-of-the-art coreference resolution system that at the same time also solves about 90% accurate what we call hard coreference problem. I'm going to finish with one quick additional example that comes from the domain of quantitative reasoning. Quantitative reasoning is really important. We do this all the time when we read the newspaper, when you look at stock results, when we look at casualties, as I had in my previous example. For example, here is a title that I've seen just a few months ago during the Chicago mayoral elections. It says that the Emanuel campaign funding totaled 3 times that of his opponents put together. When we read this, we actually, all of us, think about an equation that goes something like E is 3 times the sum of all the OIs, or maybe an approximate version of this. But how do we do this? How do we map this text into an equation that actually makes sense? I'm going to skip this example and just talk about how to map text to expression. So if you look at this 5th grade algebra problem, our goal here is actually to map or to parse this problem into an expression tree. What we've done over the last year or so is developing some method to do this. Essentially, the idea is to identify what are the quantities that are important in this problem and what is unimportant, the 2 in this case, and then figure out a way to map it into what we call an expression tree. The key observation in this theory is actually proving a uniqueness property that shows that actually one can decompose this text into pieces that actually involve 2 types of things: the group of relevant quantities and the irrelevant quantities. And this allows you, again, to put together an objective function that part of it scores all those quantities that are irrelevant to the expression, and part of it scores all those pairs of quantities that are involved in some operation. And I want to optimize this, or argmax this, subject, again, to some expectation that I have. In this case, some of the expectations are legitimacy. I just want to make sure that what I construct is a legitimate expression tree. But more importantly, I have some expectation from the answers that I read of the text. Sometimes my expectation is that the answer is positive. Sometimes it's an integral answer. Sometimes maybe I have expectation on the range of the answer. And I want to be able to incorporate all these into a computational approach that allows me now to map to the optimal decision tree. So these are expectations that really are developed given a text snippet and govern the solution. Altogether, it results in a state-of-the-art result on multiple types of arithmetic word problems. And in fact, we are doing better than 5th graders on these problems. Okay, let me conclude. I was trying to make a case for thinking about natural language understanding as a common sense inference problem, and to make the argument that we would gain by thinking in a unified way on learning, knowledge, both representation and acquisition, and reasoning. And as an example, gave a few recent samples from a research program that addresses these 3 aspects: knowledge, reasoning, and learning, via a constraint optimization framework that guides best assignment inference as a way to satisfy output expectations. So a lot more stuff is being done with this framework. You can check out our tutorial tools, our programming language, LB Java, and thank you.
Thank the speaker. Unfortunately, we don't have time for questions. Write down your thoughts and talk to Dan at the break. The next speaker is going to be Lucy. I should say the next speaker is going to be Lucy Vanderwendy, who is an NLP researcher here at Microsoft.
Thank you, Dan. Now, let's see, green button. Is the mic on? Yes. So the title of my talk is what can you go back? Wait, I can go back. What can language tell us about common sense? Now, the title of my talk has been chosen quite intentionally because what I want you to already have in your mind is that language tells us something about common sense, and I just want to talk to you about what it tells us about common sense. I'm not asking, does it have something to do with common sense? I'm just saying that it does. It's very annoying. It must be on timing. The fact that language has something to do with common sense is not straightforward. Many people have said that because every person has common sense, such knowledge is typically not communicated, and that we don't expect to find it in language. And I've taken here a quote from Liu and Singh, but there are many such people. Doug Lennett is definitely one of the people who held this belief. So I'm telling you that language does have something to do with common sense. Now, let's look at language. I'm going to eat a fish with bones. Now, this is quite similar to an example that Dan just showed us. You're not confused by this. I'm going to eat a fish with bones. The fish has bones, right? Now, if I change something very small, I'm going to eat a fish with chopsticks. Again, you are not confused by this. You know you're going to use the chopsticks in order to eat the fish. So we go through language. We're not, unless we're linguists like I am, you're not very confused by language. But language is ambiguous, right? If I put them together, side by side, I think you'll appreciate the ambiguity. I'm going to eat a fish with bones. I'm going to eat the fish with chopsticks. Now, this is fascinating to me. It always has been. That's why I became a linguist. But my question to you is, how did you just do that? What is it that you used to get that interpretation, these two very different pictures in your mind? Now, if you know the language, if you are a good speaker of the language, you're like, well, I just know this. This is common sense, right? If you don't know the language, you're going to have to look things up, right? If you don't already know the word chopsticks, maybe you've never encountered the word chopsticks, you're going to have to look it up. So let's have the computer look things up. So we look things up in a dictionary. A dictionary has recorded the common usage of our language, of any language. And again, it's recording what is common. Whether we call this common sense, I don't know. But the dictionary contains a lot of information that people might think of as common sense. So the fact that chopsticks is a pair of sticks that are used as tableware to eat food with, you can say that, okay, chopsticks are used to eat. Similarly, if I'm dealing with the fish with bones, I know that bones are part of a skeleton, which is part of the vertebrate, and a fish is a vertebrate, so I know that fish have bones. These are some of the allowed meanings of the word with, instrument, and part of. So if we can do this for a few words, we can do this at scale. We can look in our shared repositories where people have tried to encode the information that we know about words. And as Josh Tenenbaum was saying earlier this morning, what we know about words is we know about the words and the relations between the words and what the objects in the world that are denoted by these words have in common. So this is the project that we worked on which we called MindNet in the 1990s. And if there's time later on, you can ask me why we kind of stopped working on that, but I'll set that aside. MindNet we got our natural language processing system, which is underlying the word grammar checker, to process dictionaries and encyclopedias and other resources that are kind of embody standard common knowledge. We did this at scale. You can see this is a small fragment. It's a connected graph centered on bird. From this, you can see that bird, for example, has part wings. It's got feathers. It's a kind of a hawk. The hawk has claws. That on the far left, you can see that we extract the fact that pecking is by means of a beak. A beak is part of a bird. It can be part of a turtle. A beak is a mouth. The mouth is located on the face. All of this information you might have thought of as common sense, but really it's already recorded in the dictionary. And so that's one reason why we feel strongly that language does communicate a lot of common sense. And it always has. And so there are resources, as Dan mentioned, ConceptNet, that is trying to do this by eliciting this from volunteer contributors. But our thesis has always been volunteers have already contributed much of this information in the form of text. But wait, you might say, language is ambiguous. How am I using language in order to extract the common sense that I need in order to understand the language? Well, it is ambiguous many times. So bullion is bars of gold and silver, and clove is the unopened flower of a plant, tropical Asian plant. Of is highly ambiguous. But it's not always that way. So a definition of flower is the part of a plant. So I now have a very explicit, a privileged relation, part of. And gold is defined as the coinage made of this. Again, made of is a trigger for a particular type of relation that expresses material. So I can now use the unambiguous statements in language to extract information that I can then use to extract information from the more ambiguous statements in the dictionary. And I can do this iteratively, and that's how we built MindNet. And MindNet is, in fact, used. It's a very powerful resource. We use it all the time for prepositional phrase reattachment, for relative clause reattachment, coordination attachment. All of these things that Dan mentioned need this type of reasoning. So I wanted to talk about this, and then I wanted to say, what else can language tell us about common sense? Now again, by implication, I've already stated that language does tell us something about common sense, and I hope to have convinced you of that. But what else does it tell us? Well, what do we communicate? I mean, Pushsing was right. We don't normally talk about what is common sense, because that's what we share. We're not saying anything surprising or new or interesting to each other, but we talk about exceptions, right? So you'll never find in the dictionary that a bird is defined as a creature that can fly, but you'll find that a penguin is defined as a creature that cannot fly, a bird that cannot fly. So the exception proves the rule, and that's a lot of what we talk about. So as a linguist, I am interested in teasing apart what it is that language tells us of our underlying assumptions. And that's why I'm interested in how language can be used to expose or to reveal as a detective what common sense might be. There are other such, let's call them tells in language. With poker, you have a tell if you kind of reveal what you have. Sorry. So there's factives. The ancient Egyptians knew that scorpion bites could cause serious illness. From that, I can infer that scorpion bites cause serious illness. Even if it had been the ancient Egyptians didn't know that scorpion bites can cause serious illness, I would still have communicated to you the fact that scorpion bites cause serious illness. Sorry, it's on automatic timing. These fragments with temporal adverbials, these fragments are exploded when gases build up inside a volcano. From that, I can infer that gases build up inside a volcano. that's just background information that I have now contributed. I don't know how to stop it, I apologize. Dogs which hunt in packs, this is a non-restrictive relative clause. I'm communicating the fact that dogs can hunt in packs, whether or not the other part of the sentence is true. And finally, there are some interesting phrases that are, but luckily, which again, it communicates surprise. It communicates what we didn't expect, from which we might infer what we do expect. So here, finally, he had a nasty burn, which took a while to heal, but luckily didn't leave a scar. So I can infer that typically nasty burns, I expect, will leave a scar. And these are the things that I'm interested in using language for in order to extract the common sense that hopefully we will then use to solve these language ambiguity problems. So setting that aside, I think about questions a lot, question generation. And I find that questions are also telling of common sense. So here, I wanted to mention the work that's already been mentioned earlier this morning, collaboration between Virginia Tech and Microsoft Research that talks about this visual question answering, where we have a body of human-authored questions that are intended to kind of stump a computer that has been where the humans have been told, yes, this computer knows about objects, it knows about properties, stump the computer. Now, if we look at that, what kind of questions do people choose to ask? If I look at this room, I can ask 1,000 questions, but which question do I in fact end up asking? So here I found, when I looked at this data, people tend to ask about the photo elements that are surprising to them, that are not as per what I would expect. So if for the question, the set of questions that are, what color is the fire hydrant? If I ask this question to you in the audience, without seeing the picture, you're going to say red if you're from the United States, by and large, right? Always, by and large. But in fact, this question was asked for this picture where the fire hydrant is orange and white. That makes sense because this is what is surprising. So it's very like the birds fly case where I'm asking a question exactly because it doesn't match my expectations. And so I can use that information to then extract kind of what might be some of the expectations. Now, finally, I'd like to just talk about beyond language. What happens when we go away from language? Because if you're using language to solve language, you're very circular and you don't know when you're kind of done. So I was hiking last week and I was meditating on this common sense. And so I knew that one of my examples from the web was some of us felt the force of lightning, but luckily none of us got hurt. Okay? So lightning, from here I can extract that lightning usually causes people to be hurt because there's some surprise that nobody was hurt when we felt the force of the lightning. So if I have a prime directive of don't get hurt, how do I avoid lightning? Where's the common sense that tells me what to do? Now, we kind of all know, okay, don't be out on an open field, don't be out on the water. But where is that information contained? How did we learn it? And can we even agree that that's what we would call common sense? And when I was meditating on this, I really thought that what is separate from the dictionary is the sense of common sense where it allows the members of the community, the common set of people, to infer, given a situation, to infer what might have happened prior to that situation and to predict what might happen. And I will say that because in the natural language processing community we have focused on dictionaries where such resources have already been recorded for many centuries already, we have taken a more taxonomic approach to what types of information can be extracted from text. Again, objects and their relations. We have been less good at extracting information about the temporal relations. And right now, I do not know of any robust resources, though I should look at the predicate templates that Dan just mentioned, that capture temporal relations and causality, which is what would be needed to make inferences and to predict. Also, I don't know of any robust resources that really capture the complex scripts that we use to frame our experience, which goes back to Winograd, the restaurant script. If I walk into a restaurant, the waitress, okay. So I have a whole set of expectations. We do not have a robust resource that captures what are the set of expectations for any situation. So the questions that I came up with as I was preparing the talk are, one is, I'm not quite sure whether we can distinguish common sense from situational, contextual experience and awareness. I really don't know how to make that distinction if it's not about the words of the language. And then because we're talking about common and that it's also, it must also be per community. If we have a community of computers, is our human common sense really necessary or sufficient or even overlapping with what the common sense will be that a computer will need? So those are my questions. And now maybe some time for your questions, I think. Yes, there is some time. Okay. And I apologize for the unnecessary flipping of the slides.
Questions for the speaker?
I just want to do a quick clarification just for history, since this goes back to my history, but scripts were Schenck and Abelson, not Winograd.
I apologize.
Yes, I knew you knew, but
Thank you. Yeah.
Similar time period.
Thank you.
Hi, I really enjoyed your talk very much. I'm interested where in common sense, social schema like gender or ethnicity, these kinds of very specific assumptions we make about things as a community, where do those come in and how do you analyze those?
So I have not thought of those. As you can see, I've been more focused on extracting the information of what the language tells us. So if we can find phrases or tells that will kind of reveal some of these gender issues or social issues, you'll probably see the, but. But is very powerful. It can change the basic understanding completely with one single word. So I might expect to find some of those tells in if I wanted to specifically look at that, but I myself have not looked at it. I know Ben is going to go into kind of a more rich definition of common sense than I've been working with.
Hi, Lucy. You mentioned obliquely that something like you weren't working on MindNet and someone should ask me about this. So I am curious about that because it was one of the early, like James Allen is now doing this sort of thing again, trying to extract by language things from WordNet, synset definitions and examples. Mm-hmm. So what's the story there?
So the story is, and I'm pleased to, I have 1.5 minutes. So there were 2 questions that caused me to stop working on MindNet, or caused me to really question myself. One was, what is the correct set of relations that hold between the objects? And I think we don't yet have a good notion of that. There's no way to decide. I myself, my thesis work was on noun compounds, and so there were approximately a set of 30 relations that were particularly useful for doing that thesis work. There's no reason why we don't have more or less. So, well, less is a little bit tricky, but there's no reason why we don't have more. And so I really was hoping to work with people on trying to induce the correct number of relations from the text itself. And I think we're getting somewhere closer to that. I'm working with some people in biomedical text processing where we're doing kind of some hyper-edge detection that might go in that direction, but we haven't gotten that very far with that. So that was the first. And then the second was that currently our language processing, the notion that we have of constituent structure is not yet rich enough. And this goes back to Dan's problem, where it should have been Piet. If Piet is a black Dutch man, I have a notion of the black, or the Dutch man is a unit. I can't really pull that apart. And it's the, you know, kind of, we used to call it the boxing problem. So how, what is the necessary part of this noun phrase where this modification makes a difference to the denotation in the world, and which are the additional informations, which are kind of the non-restrictive relative clause information that I don't need. So natural language processing does not yet have a structure which is good enough in order to do that. That was our opinion at the time, and I still hold that opinion, but I'm willing to be challenged. But now my time is over, so we should hand over to Ben. Thank you for the question.
Let's thank the speaker. And next up, we have Ben van der Mee from Johns Hopkins University.
Mic's on, yep. Hi, so I'm going to be talking about, like most of the other panelists, common sense and language, where I'm coming from this perspective that's been shared for 50, 60 years and the last sort of hour and a half, that the way that we communicate is very closely tied with this shared notion that we have about the world. Okay, so first, I'm going to say a little bit about why we think we might need common sense for language. And then I'm going to move from there on how we might be able to use language processing tools to then automatically acquire common sense knowledge. Okay. So first, a couple of definitions. We've sort of been moving through this panel without trying to be a little more crisp of what we're talking about. Shared knowledge, we're going to define as if I know some proposition P, and you know P, and I know that you know P, and you know that I know P, then we're going to say this is shared knowledge. And shared knowledge is usually going to talk about something that maybe a few of us know. Okay, so there's a particular fact, like what's the date of my birth. Most of you don't know that. But if we move to a larger group, we start talking about background knowledge. So we're all technologists, and there are certain things that we can talk about amongst each other very quickly and efficiently that we can't do if we were to, say, go and bump into someone on the street. It would take a much longer time to try to explain something. Now, if we move that group to be very large, now this is called what's commonly known background knowledge, or just sort of common sense. All right, so this is if I go out on the street, I bump into someone, if they speak English, then I'm going to immediately start assuming that they know things like the sky tends to be blue, or that birds have wings. Okay, this is what we mean by really simple common sense. And like I said, a lot of people have written for decades that it seems like when we're processing language, we're making use of this sort of knowledge all the time. And when we say making use of knowledge, what I mean is inference, and people have just been talking about this, like Dan, and this is the central point of his talk, where, again, now decades of people have been writing about how the act of understanding language seems to be primarily one of online inference, that as a speaker is giving you utterance after utterance, or as you're reading sentence after sentence, language itself is very telegraphic. There's the bandwidth is small, yet there's a lot of meaning that's being communicated between people, and the only way that seems to be able to happen is if we're able to constantly fill in the blanks. And the only way we can fill in the blanks is if we have a lot of shared understanding about how things are supposed to go together. Now, if we go back to McCarthy's original definition of common sense, McCarthy himself didn't really care much about language processing. He was a knowledge representation and reasoning person. But even in his definition in the 50s, you see language sort of coming out. Right, so even McCarthy's notion of what common sense meant really seemed to hinge on this notion that something is being informed of something, and you need to be able to quickly sort of infer the common sense things that should result. And indeed, one of the most cited articles in computational linguistics by Jerry Hobbs and his colleagues on the famous notion of interpretation as abduction exactly just says that the act of building a language understanding system is trying to prove the text as it's being presented. So this led folks like Schenck in the 70s to say, if we all seem to keep repeating this same notion that we need knowledge, and it really seems like if we can't nail that problem, then we're never going to be able to solve natural language understanding, and in particular, we're never going to build a real system unless we can really figure this out. So now, so we all sort of agree in the 70s that this is a problem, and so we're going to fast forward 40 years, and then we find people saying the same thing. Now, part of this comes from the AI winter that's been talked a lot about already this morning, where we sort of put aside grand challenges anyway, so it's not like everyone was banging on this problem in the last 40, 50 years, but there still were plenty of folks. For instance, a lot of people said, well, how about we just build this knowledge base by hand? And as Lucy and some others have mentioned, one of the most famous efforts along these lines was the Psych project by Doug Lennett and various other sorts of efforts. I'm not going to be talking about that here, though. Instead, I'm going to move to the notion that maybe we can acquire some of this from language itself. Okay. So I'm just going to reiterate a point that Lucy made, that really Microsoft Research was probably one of the first places that really pushed on this idea. In the 90s, they just said straight out that it seems like we should be able to acquire a lot of this. And critically, it seems like this is really the only way we're going to get a lot of this knowledge, is by automatically reading it. And there's been lots of other people that have said similar sorts of things. I've sort of roughly broken the research field into these two categories, and there's lots of research that's not up on the slides. But there are some folks that talk about knowledge with a capital K, where we're going to build a knowledge base, and we're going to do things with it that may or may not be related to language. And then there are folks that are trying to optimize for some language understanding task, where whether or not you actually think about that as language or as knowledge or just co-occurrence statistics that are helping you optimize for some downstream problem, some people don't care. And depending on which community you're in, the terminology is going to change. Okay, so now I'm going to talk about a few projects that I've been involved in trying to acquire this sort of common sense knowledge, where I've broken it up into sort of two rough categories, starting with basic properties. So by basic properties, I mean we have lots of individual conceptual class members sort of around in the world. We have Billy and Sue and Bob and Jack and Mary, and these are all members of the class person. They're also members of the class physical object and various other sort of semantic categories. And if we have examples from various documents where we see certain predications on individual instances, then we might be able to generalize that up to some property about the class as a whole. Or if we find various relations that hold between members of different semantic categories, then we can learn a sort of general pattern. And these three projects are all sort of picking up on that same theme, but looking at different sources of language data. So first, next. So this is an effort that was started by Len Schubert in 2002 and some of his graduate students, particularly myself, where Len's idea differed a bit from the MindNet project. So MindNet said, it seems like people have really written down a lot of declarative things in encyclopedias and dictionaries. Len said, that's definitely true, but it also seems like there's a lot of knowledge that's just in descriptions of the world, because people are talking about ground instances out in the world, and if we can recognize that these are all just basic descriptions of individual instances that seem to be repeated often, then we should be able to lift this up into generality. So, for instance, if we take some long sentence out of the Wall Street Journal, this is very grounded. This is talking about a lot of very specific things. And the standard sort of notions of information extraction, like the KBP kind of work that Ray was talking about, would want to know that exactly it's Representative Rane Filippo, and he's coming from a particular place that he represents, and so on. But what we're talking about here is that we want to be able to automatically process this with sort of syntactic parsers and semantic parsers and get a structural analysis where we can then gloss that into English, where rather than facts that would go in something like Wikipedia, we want this sort of more general common sense. For instance, if we automatically recognize that the string Representative Rane Filippo refers to an elected representative, and we know that that elected representative is the one doing the saying of this longer string, and we know that that longer string refers to something that we're just going to abstract up as a proposition, then we get this sort of general notion that elected representatives like to say things. And this seems like a bit of common sense that most of us share. Or as another example, if we recognize that the string Ronnie tends to refer to male individuals, then we can learn that in general it might be possible that a male individual may be impressed by admission. And so if you can get 1 or 2 or 3 or 4 sorts of possibilistic statements that you can lift up out of each sentence, out of say a New York Times article, there's a lot of New York Times articles and they have a lot of sentences, and so then you can start trying to bootstrap up a lot of these sort of general things in the world. And this is a project that's been going on for quite a while at Rochester. So from declarative statements about the world, we're going to move over to questions, where this is an effort that began around the mid-2000s at Google Research, with myself and led by Marius Pashka, and he continues to work on this line, where the underlying intuition is that there are millions of people asking millions and millions of questions to search engines like Bing or Google, where if we can recognize that China, France, Spain, USA, and Denmark are all instances of a general class country, and we see that it seems like people keep asking the same sort of basic question about these instances of the overall class, then we can learn that, well, maybe it's the case that generally a country may have a capital. And there's all sorts of properties that you can learn in this way. Search engine query logs are a really great 21st century resource. Unfortunately, as common researchers, we don't have access to that. But if you're at a place like Microsoft or Google, it's just a really rich source of this sort of information. I'm going to focus on country just for a second and go back to the 70s. There was a linguist named Ellen Prince that also talked about this notion, but she referred to it as the stereotypical tacit assumptions. And she exactly described this scene of like, I'm on a subway, I'm going to bump into someone, and if they're from Chicago, then I might have a tacit assumption that if I'm also from Chicago, then we might know who the mayor is. Much like the technologist sort of setting here, we sort of share that sort of background knowledge. But no matter where this person is from, I should be able to assume that they have access to the following sorts of information, and she hand writes down these bits of tacit assumptions. So we go back now to the sort of properties that we're learning automatically from search engine query logs, and I find this heartening. So someone in the 70s said, it seems like this is knowledge that people have in their heads. And I say, well, it seems like this is things that we can actually extract automatically. Right? So at least there's some forward progress. So from query logs to social media, much less formal. And this is based on the work of a number of postdocs and graduate students at Johns Hopkins, now some of them at Microsoft Research. So we all know what social media is. Social media is primarily a lot of random people saying a lot of random things about their everyday lives. All right, so this is not like a New York Times article that's going to go in detail about something that's particularly important. In bulk, the sort of information on social media is just people sort of saying things that they did today. So they're just sort of moving around doing normal things, and maybe it would be interesting to know what they're talking about. So there's a category of researcher that is very interested in trying to predict underlying semantic classes. Just to say, I think that this set of Twitter users is male, and this set of Twitter users is female. Or maybe I think this set is above 25, and this is under 25. And this is very useful for things like politicians, because you can try to predict maybe who's a Democrat versus Republican, and try to figure out what sort of topics each category is talking about. Knowing who's above 25 versus under 25 is going to help you place ads, for instance. But lately, we've been thinking a lot about this notion that we can maybe do more fine-grained social role classification. We have a few experiments along these lines where if we could predict someone that was a college student or a baker or a butcher or a candlestick maker, then we can start asking, well, what are properties that are characteristic of those classes? And this is the same sort of idea for the previous two projects. I want to be able to lift up from individual instances. Now these instances are Twitter users, and I say, what are the sorts of things that they talk about? And if I think of this sort of subset of the Twitter population with some probability might be a reporter, and they tend to talk about one thing in particular, like articles, then I can start to associate the notion of articles as something that a reporter has. And similarly, the sorts of activities that members of these classes participate in might somehow be characteristic of those classes as well. Okay, so from these sort of basic possibilistic statements, I'm going to move to combinations of these. Okay. Now, first going back to the 70s once more, Minsky had this notion of a frame. Many of you have heard of this. It was a very, very big deal. Lots of people sort of followed up on it, where the notion was that I want to be able to So triggered based on some bit of context, I want to be able to use 1 or 2 bits of salient information to then rapidly index into other information that should be salient given that same context. And Schenck ran with that idea basically the next year, which then led to the 77 paper by Schenck, the book by Schenck and Abelson, talking about scripts. So scripts, Schenck defined directly as just a type of frame that was more like episodic. There's lots of people now in the computational linguistics community that are really eager to try to automatically learn these scripts, much the same way that we were learning more simple propositional statements. Some of this work has actually been done at Microsoft. Lucy's involved with it, along with Huifeng Poon. I've been concerned with it initially, mostly on an issue of scalability, but lately we've been trying to tackle it more directly, where the underlying idea is that if I have some relation in text where then I then have some other relation in the same text where the argument seems to be shared. And then I see these same sort of things repeated over and over again. Then I can start inferring, well, maybe if a particular thing happens to something, and then I might be able to expect that this other thing might be able to happen in the same context. So for example, if we saw a lot of sentence pairs like this, then we might want to be able to learn this general sort of notion that in the context of someone studying hard for an exam and then them doing well, then we shouldn't be surprised if the teacher then says, thumbs up, good job. Okay, this is something that none of us, that all of us should sort of expect might happen. So again, we're going to do this in the same sort of way, where we take big piles of sort of clean grammatical text, and it's important that it's clean grammatical text, and especially that it's in English, because that's the only language that the community can actually process very well. Because we need to process it very heavily with a lot of syntax, semantics, in particular co-reference, which Dan was referring to earlier, which allows us to link across statements in multiple sentences. Where then we're going to throw it at a generative model for there's some generative narrative stuff, which I'm not going to talk about. And then I'm going to focus in on this discriminative model for a moment, mostly just to sort of touch up the last point I'm going to make, where this model that we were using, we just pulled off the shelf a state-of-the-art discriminative language model and did some slight modifications. And in a very short period of time, we were able to get very strong state-of-the-art results on a standard evaluation metric known as the narrative close, which many folks have sort of been using as some way as a proxy of measuring how well you're doing at script induction. Now, the fact that we were able to do so well on this based on a discriminative language model is actually very concerning to me. It's great to get state-of-the-art results in anything, but it makes me question the utility of this metric because of something I'm going to refer to as reporting bias. Reporting bias are otherwise known as the blinking and breathing problem, which is to say we never talk about blinking and breathing. And so if we look at just basic frequencies pulled off of, the Terra word is a Google Ngram collection that Google released to the community about mid-2000s. And so we can just do a naive survey of just various verbs that people are using and say that it's scary to think that people might be murdering at the same order of magnitude as laughing, but clearly that's not the case. Or that murdering happens at an order of magnitude more than blinking, or that the fact that inhaling happens so much more often than exhaling. Right? And so looking at these frequencies, like now that we look at this in post hoc, it's very easy to say, well, yeah, of course we don't describe the world as sort of this uniform probability. Our texts aren't generated by just sort of picking some little space-time interval of the world randomly and then randomly generating true statements about it. There are certain things that we want to write about for particular reasons, and there's only certain things about those situations that we write about with any real frequency. And so as we start building models that get more and more accurate at their ability to sort of induce knowledge from text, and we're evaluating them based on text, this is, I think, running the risk that what we're effectively doing is building really nice structured language models, which is going to be useful for lots of language processing tasks, but that's not necessarily that we're actually learning real-world probabilities about how likely things actually are to obtain. So with that, lots of people think that we need knowledge. Lots of people think we can get it from text, but there's this disclaimer that maybe we need to be a little bit careful about what we're learning. So thanks.
Questions for Ben?
Hi. So, you said at the end that you'd be more interested in sort of what the actual probabilities in the world were as opposed to, hi,
thank you.
we met at breakfast this morning,
Yes.
then sort of what the probabilities in the language were. And you raised the point that the difference is due to the fact that there's only certain things that we choose to talk about for certain reasons. And I guess I'd like to focus on the latter and maybe get your thoughts on where is that in our current research programs on language. Why do people choose to say certain things and not certain other things?
Boy, why do people choose to say certain things versus other things? I mean, the quick answer is going to just be punting back to statements made by Lucy that, so we talk about the surprising things primarily, or we talk about the important things. And so it's going to be some combination of just sort of social utility that we communicate for a reason, and often it's to express things that are new. Sometimes it's to fulfill some other sort of social good. So I might tell you lots of news stories about crime in a particular region, even though that crime may not actually be that very likely, but I might really want to be able to get extra funding to hire more cops. And so I can bias my use of language. I mean, certainly these are things that people do all the time in order to try to get something out of it. But that's an entire field of social linguistics, and I'm not really qualified to say more than that.
So really great talk, and I love the research program that you outlined. I have two concerns I wonder if you can address. One is about mapping the various items that you were describing as learning from language to more formal predicates, right? If we don't do that, there's a worry about canonicalization, and the fact, right, you were showing how from a single sentence we can learn a lot of useful things, but I wasn't clear on exactly the vocabulary. And the second point, and I think it's a related one, is one about precision, right? You're saying we need to process sentences, we need coreference to work. Of course, state-of-the-art coreference is not super high precision. So the second concern I have, and again, not about your work in particular, about my own work in the community, is just, do we believe that we can achieve high accuracy, and if so, how?
I think we can achieve some level of accuracy. I think actually the more important question is, what is this good for anyway? Right, so there's been lots of different, I mean, I didn't touch on that at all here. I was just going to talk about common sense and world knowledge. But what's the downstream task for anything approaching a formal knowledge base? I know that you have a task that you care a lot about, and so that's a good example of something that we could then try to evaluate. So we want to be able to answer questions for a science exam. Whether or not we can do it accurately enough, I think there's been decades of people staring at knowledge bases that they've automatically acquired and then evaluating them on some sort of intrinsic notion of this looks good, this doesn't look good, this is kind of an error. And I think that's actually all wrong. And I did plenty of that before, and this is why I took a hiatus on some of this work up until recently. Because it's really just going to end up being task-driven. If it helps in a task, then it's useful, and if it doesn't help in a task, then it's navel-gazing back at papers written in the 70s.
Thank you.
So the capital, the countries have capitals example was interesting to me because the capital term is one where it's really defined as a role something plays, and of course there's nothing in there that learned what a capital is, just as something that companies and of course we also know states and things have. And it's a term that can only be probably learned by noticing, oh, it seems like all the government things happen in capitals, announcements. Any chances of getting to those kinds of very role terms that in some sense you have to see a script to get the role rather than learning the script?
Well, I mean, I think that some of those role terms do come out of these other efforts. So out of a question-driven framework like putting it to a search engine, you might not be able to see it quite so easily. Of course, then you'll have click-through logs. So if I click on the Wikipedia page pretty often for the state capital, for instance, then I'm going to be able to glean that signal off of user behavior. But I think relational terms you do see all the time in normal text. So I can see that Albany is the state capital of New York, and I mean, and there's a number of people in the room here that do that sort of relation extraction. Oh, to be a capital. I see. Well, to be a capital is to be someplace that tourists visit, I think is what you're going to see on out of text statistics. And that's all I got. Yeah, hi, Peter.
I think there's a question underlying, a lot of the work in this session and also in the field more general, which is So we need common sense to understand language. Everybody agrees with that. But now the question is, can we acquire all the common sense that we need to understand language from language? And if not, what else do we need to do?
That's exactly the right question. And I believe we cannot get all the knowledge of the world by reading. I do not believe that any notion of reading text is going to completely give us everything we need. I'm looking forward to roughly 10 years from now when those drones in the morning are perfectly safe. Honestly, like once we have lots of very cheap, omnipresent sensory devices that can just be everywhere and actually can start taking uniform at random snapshots of things that are going on in the world, that's when we're going to be able to really see the promise of grounded language that I think is going to be talked about in one of the later sessions. So I mean, we really need to have embodied agents.
We're about out of time. Is there any last question?
So, very nice talk. One very interesting point you made in the middle was language being a tool that is very useful, or was very useful, or is very useful in the future, due to the limited bandwidth that it accords. Do you think that as bandwidth increases for consumption across multimodality and media, the tools that we have developed in the language understanding world will then augment, or will we need an entirely new way of thinking now that the bandwidth may be bigger?
I'm having a hard time parsing that. So I'll just go with a quip that probably completely misunderstands the question, that nowadays the tool is just a neural net, and we can just buy more GPUs, and we're going to use that for language, we're going to use it for vision, we're going to use it for every other bit of sensory information. And so, yes, our tools will scale. And ask me again after the session if that's not the right interpretation.
All right, let's thank the speaker.